In my last class, we have defined the concept of eigenvalue and eigenvector of a linear operator defined on a vector space V. If the dimension of the vector space is finite, then I have also defined the concept of eigenvalue and eigenvector of square matrix associated to linear operator defined on finite dimensional space. We have taken some examples. We have seen in some case the eigenvalues, linear matrix may not have eigenvalues, in some case it has eigenvalue. Then we have also seen how to find the eigenvectors associated to the corresponding eigenvalue. If you recall, I took last time this is the matrix A 3 1 minus 1 2 2 minus 1 2 2 0. We have seen the characteristic polynomial of this matrix is C minus 1 into C minus 2 whole square. So, C equal to 1, 2, 2 are the basically eigenvalues of the matrix A, and the eigenvector associated to eigenvalue C equal to 1, we have calculated last time V1 equal to 102 transpose, whereas for eigenvector associated to eigenvalue 2, that is 112 transpose. Here A minus 2I, if we consider this matrix, then I have seen that rank of this matrix is again 2. So, it has only one linearly independent solution, A minus 2I operating on x equal to 0. So, I have only one linearly independent eigenvector associated to eigenvalue C equal to 2. Now, let me consider another examples. Let V be the space of all continuous real valued functions defined on real line R. So, V be the space of vector space of dimension infinity, please. Consider a linear operator T on V defined by Tf(x) equal to 0 to x ft dt. So, this is the definition of the operator T on V, please. We have already seen this function T is a linear operator on V, please. Claim T does not have any eigenvalue. T does not have any eigenvalue. So, how to prove it? Suppose T has eigenvalue, say lambda, then there exists 0 not equal to f belongs to V such that equal to lambda times f of x. It has to be like this. So, this implies 0 to x f t dt equal to lambda times f of x. It is given to us f is continuous. Since f is a continuous, so the function 0 to x f t dt, this integral is differentiable from the fundamental theorem of the calculus. We can say it is a differentiable. So, differentiating both this side, we have f x is equal to lambda times df by dx. I can also add, if it is confusing, I can say that it is a all continuous real valued even differentiable function also. So, that f x equal to lambda df x. If lambda not equal to 0, so there are two possibilities, the lambda equal to 0, lambda may not be 0. If lambda not equal to 0, then we have df by dx equal to 1 by lambda times f raised. So, this implies f equal to some constant c 1 times e to the power 1 by lambda into x. I mean, that is f of x equal to c 1 e to the power x by lambda. Now, we see that at x equal to 0, if I use the initial condition at x equal to 0, f x equal to 0, because f x equal to 1 by lambda times integral 0 to x f t dt. So, if x equal to 0, so certainly f 0 equal to 0 from this definition, please. F 0 equal to 0 from star. So, this implies that f equal to 0, which contradict the hypothesis f n equal to 0, since f is an eigenvector of t. So, this is not possible. Now, if lambda equal to 0, this case for lambda equal to 0, what we have, then star implies f x equal to 0. So, this implies f equal to 0, because if lambda equal to 0, integral 0 to t x f t dt equal to 0. So, differentiating I will have f x equal to 0, please. So, I will have f equal to 0. So, again f cannot be an eigenvector of t. So, we see that both the case when lambda equal to 0 as well as lambda not equal to 0, the operator t does not have eigenvalue. So, let me take another linear operator on the same space. Consider the differential operator d on the space of real valued continuously differentiable functions. So, the space is again infinite space, and we have considered the operator as d, that is differential operator. Then we have for any p, I can say p x belongs to the space V, that is space of differentiable functions. So, D is operating on V to V is mapping P goes to dP, that is equal to dP by dx. So, if I consider this differential operator on this space, we have for e to the power ax which belongs to V and D operating on e to the power x ax equal to a times e to the power ax. So, this implies a is an eigenvalue of D. So, in this case we have the operator has eigenvalue even the space having dimension infinity. Let me take another examples. Let T be a linear operator on Rn, I mean space of n tuple, such that the matrix representation of T with respect to standard order basis this is capital B, which is given by say B equal to, okay. So, let me take here n equal to 3 space of 3 tuple. So, B equal to I have taken as 5 minus 6 minus 6 minus 1 4 2 and 3 minus 6 and minus 4. We have determinant of B minus C I equal to determinant of 5 minus C minus 6 minus 6 minus 1 4 minus C and 2, the last row will be 3 minus 6 and minus 4 minus 6. Now, this you can immediately check, this will be again something like C minus 1 into C minus 2 a whole square. So, for this matrix the characteristic polynomial is exactly same what I consider that first matrix A 3 by 3 matrix, that is a matrix representing some operators. So, both A and this present matrix B have the same characteristic polynomial. So, this implies eigenvalues of B are 1, 2 and 2. Let us quickly see what is the characteristic vector associated to 1 and 2 and 2. So, characteristic vector associated to C equal to 1 should be calculated by B minus I capital X equal to 0. Now, B minus I, this is equal to the matrix B minus I equal to what? We will have 4 minus 6 minus 6 minus 1 plus 3 2 3 minus 6 and minus 5. So, B minus I equal to this matrix. We can quickly check the rank of this B minus I equal to 2. Rank of B minus I equal to 2. How to show it? So, that we can do through elementary operations. Anyhow, we have to do to find the eigenvectors. So, for this I can rewrite this is say 1 minus 3 minus 2 3 minus 6 minus 5 4 minus 6 minus 6. If I do this elementary operations, I am getting 1 minus 3 minus 2, multiplying first row by 3 times and then subtract. So, I can simply multiply first row by minus 3, then I am getting 0. So, minus 3 9 and 9 plus minus 6 will be plus 3, then 6, this is plus 1. This is again I can do the same by multiplying first row by minus 4 and then adding, then it will be minus plus 12, so it will be 6, 8, it will be 2. So, we see, so this will give you 1 minus 3 minus 2 0 3 1 0 0. So, rank of this matrix B minus I equal to 2. So, this implies I can find the solution will be your equation x1 minus 3x2 and minus 2x3 equal to 0 and 3x2 plus x3 equal to 0. So, this implies that x3 equal to minus 3x2 and here I am getting x1 equal to 3x2 and plus 2x3. So, this implies x3 is equal to minus 3x2, it will be basically equal to, so again minus 3x2. So, x3 is equal to x1. So, this implies if I substitute x2 is equal to 1, I am getting x1 equal to minus 3, 1 and 3, minus 3. So, this transpose will be eigenvector of the matrix B. So, I am getting, or I can write out a plus, then it is minus, this is plus. So, this implies 3 minus 1 3 is an eigenvector of T associated to 1. And let me represent that alpha 1 equal to 3 minus 1 3. Eigenvector associated to C equal to 2, that we can calculate by same way, and this is equal to again B minus 2I x equal to 0 implies I will get 3 minus 6 minus 6, 3 minus 6 minus 6 minus 1 2 2, 3 minus 6 minus 6 into x1 x2 x3 equal to 0 0 0. So, this implies immediately I can see the rank of B minus 2I is 1, because all rows are basically scalar multiple of each other. So, this implies I will have 2 free variables. So, I will have 2 linearly independent eigenvectors. So, this implies we will get 2 linearly independent eigenvector associated to C equal to 2. Let me consider alpha 2. I am sure you can find out the what about the 2 linearly independent eigenvector exactly same way what I did for the C equal to 1. So, let me write down the final solutions. Say alpha 2 equal to I will have 2 1 0 and alpha 3 is equal to 201. So, I will get two linearly independent eigenvector like this. Let W2 denote the space of eigenvectors associated to C equal to 2. So, that is W2 is equal to linear span of alpha 2 and alpha 3, and let W1 equal to linear span of alpha 1. So, then W1 and W2 intersection of these two subspace, we already know that for different eigenvalues the eigenspaces, if we consider intersection of the two eigenspaces W1 W2 will be 0 subspace. This implies if I consider B equal to italic B equal to alpha 1, alpha 2, alpha 3 is an order basis for the space V equal to R3, where alpha 1, alpha 2, alpha 3 and alpha I equal to 1, 2, 3 are eigenvectors of operator T. I can also say that here alpha 1 transpose, alpha 2 transpose, alpha 3 transpose are eigenvector of the matrix B associated to eigenvalues 1, 2 and 2. Now, consider a matrix P whose columns are alpha 1 transpose, alpha 2 transpose, alpha 3 transpose. So, I have considered matrix 3 by 3 matrix which columns are alpha 1 transpose, alpha 2 transpose and alpha 3 transpose. Then we have B into alpha 1 transpose is equal to 1 into alpha 1 transpose, B into alpha 2 transpose equal to 2 into alpha 2 transpose, and B into alpha 3 transpose equal to 2 into alpha 3 transpose. So, this implies B into this P equal to, I can write down P into 1 0 0 0 2 0 0 0 2. So, I have BP equal to like this. Here this P matrix is invertible because they are alpha 1, alpha 2, alpha 3 are basically linearly independent. So, the corresponding columns will be also linearly independent. So, this implies if I multiplied P inverse from the both sides, I am getting P inverse BP equal to a diagonal matrix 1 0 0 0 2 0 0 0 2, which I am denoting as a diagonal matrix tree. Okay, so, what I find here, when two operators define over the same spaces, that is R3, and both the operators with having, suppose they have matrix representation with respect to standard order basis, say capital A and capital B, even though they have same characteristic values, but the nature of the operator or nature of the corresponding matrix representation are different. First matrix, what I considered in the very beginning, A, we have seen it has only two eigenvectors associated to eigenvalues 1, 2, 2. So, we did not have any scope to write the first matrix A as some, we could not find any invertible matrix P such that P inverse AP equal to some diagonal matrix. But for second operator which has matrix representation with respect to standard order basis of capital B, we see that this capital B is similar to a diagonal matrix, even though both the operator have same characteristic values. So, having same characteristic values does not mean that the operator or matrix will have same nature. Another important thing is what we have found it here, that if an operator is defined over a finite dimensional space and the field is complex number, we have the characteristic polynomials which is factorizable over the complex field. Therefore, the linear operator will have eigenvalues. But if I consider infinite dimensional space, then even this space is defined over the complex field, then also the linear operator may or may not have eigenvalues. That already you have seen through these two examples. So, now let us try to understand what is the use of studying eigenvalues, eigenvector of a given linear operator or a matrix space. Introduction of this eigenvalue or eigenvector is basically we are looking for the answer of couple of questions. Let me write down the question please. Okay. So, there are a couple of questions that can each linear operator T be represented by a diagonal matrix in some order basis? Because we have seen in our last examples matrix A is not diagonalizable. I can say that it is not similar to a diagonal matrix, but B is similar to a diagonal matrix. Second question is, if not, for which operator T does such basis exist? Third is, how can you find such basis if at all exist? If not, then what is the simplest type of matrix representations of T has and how to check it, please? To answer this set of questions what we have raised, let me initiate by introducing a terminology called diagonalizable operator. What is diagonalizable operator? Let V be a finite dimensional vector space over the field, say capital F. It may be real number or may be complex number. Let T be a linear operator on V. T is said to be diagonalizable provided the space V has a basis consists of eigenvector of T. So, according to definition of the diagonalizable operator, if you recall the last two operators whose matrix representation was A and B, so I can say the matrix B is diagonalizable, or the operator T on R3 whose matrix representation with the standard order basis is capital B is diagonalizable. Whereas the operator whose matrix representation is not diagonalizable. Now, let me raise the question, if the operator is diagonalizable, what sort of benefit we are getting? Let T be a linear operator on a finite dimensional vector space V and is a diagonalizable operator. So, let B equal to alpha 1, alpha 2, alpha n be a basis for V consists of eigenvectors of T. So, this implies there exists n scalars C1, C2, Cn such that T of alpha I equal to Ci alpha I equal to 1 to n. Here Ci may not be distinct, Ci may be repeated. Let Ci is repeated di times, and there are k distinct Ci, that is say C1, C2 and Ck. Not to confuse, let me consider, say C1 is repeated to D1 times, C2 is repeated D2 times and Ck is repeated Dk times. So, in this case we have the matrix representation of the operator T with respect to order basis B is should be like this: C1, C1, C2, C2 and Ck will repeat it Ck Dk times. So, this means that this is equal to, I can write down, it is something like this, you know, C1 I1, C2 I2 and Ck Ik. Where Ij is Dj cross Dj identity matrix. So, this implies the characteristic polynomial of T will be what? Determinant of, suppose if I denote this is equal to, let me consider the capital D, will be D minus xi. If we say that x is a vector, then better replace instead of x say just Ci, so that not to confuse, determinant of C minus I, and this will be exactly equal to something like C minus C1 power D1, C minus C2 power D2 and C minus Ck power Dk. And if you denote this is equal to function of C, f of C, so you see that it is a characteristic polynomial of the operator T, and here sigma of di equal to n, and I equal to 1 to k, this value is equal to exactly n. Di represents algebraic multiplicity of eigenvalue to Ci, power of the C minus Ci in the characteristic polynomial will denote the algebraic multiplicity of the corresponding eigenvalue. Now, suppose we are interested to know the what about the eigenspace associated to the eigenvalue C1. To know the eigenspace associated to eigenvalue, say for sake of simplicity I take C1 only, we have to solve the system D minus C1 I into capital X equal to 0. We have to solve the systems. Here, if I consider D minus C1 I, this will give me all the rows, first D1 rows will be 0, because I am getting here C1 minus C1, C1 minus C1, then I will have C2 minus C1, C2 minus C1, and in the end Ck minus C1, Ck minus C1. Since C1 is different from C2, C3, Ck, therefore, this shows that the first row, second row up to D1 rows all will be 0 rows. Next, after D1 rows, all other rows are non-zero rows. So, this implies that I have only exactly D1 number of free variables. So, this implies there are exactly D1 number of free variables. That is exactly D1 number of zeros are on the principal diagonal of the matrix D minus C1 I, and that is the basically number of free variables, which is also dimension of the eigenspace W1. Similarly, if you go for C2 or C3 or Ck, the number of zeros in D minus Ck(i) will give you the dimension of the eigenspace Wk. Similarly, for eigenspace Wk, the dimension will be is dk. So, if the operator is diagonalizable, then we are able to say what is the eigenspaces. Immediately we can calculate what is the dimension of the corresponding eigenspaces. We can say most of the characteristic of the operator immediately. So, that is why the diagonalizability is the, I can say, most simplified structure when representation of an operator. If you say that if it is diagonalizable, then operator is very simple. However, we have also seen that there are some situations even the operator is defined over a finite dimensional space, but it is not diagonalizable. What should be the next step to understand the corresponding operator which is not diagonalizable, to understand what will be the most simplified structures? So, we will continue more in my next class, please.